Good morning, everyone. Come on in. Looks like just about everybody's here already. Sorry, it took me a couple seconds extra to get started. I don't know, my Zoom was just going really, really slow. I started at 6 till, well, 9:24, that is, and still took that long. I did post a couple videos over the weekend, but 3 of them didn't post, so I'm still making some more. Actually, that won't matter anyways. That was 242 class, not 241 class. But of course, there's plenty of videos on my YouTube channel that you can look through. Don't forget to look at the titles that I posted in the updated list of YouTube videos. You can usually tell by the title what they're from. You can also look under where it says calc, alg, or conceptual. It just says like 3 or 4 letters in each case to say whether it's conceptual physics, algebraic physics, or calculus-based physics. Right below that, you'll see that it's got like a PHY 241 or 242. If it's 241, it's something that's relevant to you guys. So that's another way you can double check. Does anyone have any questions before we get started though?
I have a question about the extra credit.
Yes.
It was labeled like it was from last semester because I had 825, I'm pretty sure. So
Yeah,
like with
and is it
that
disappear
extra,
too?
huh?
Did it disappear as well, or is it still up there?
It did not, I haven't seen it. I didn't check this morning, but last night it was there.
Okay, I think I might have erased it if it was old data because it was one that wasn't relevant to us. But
Oh, okay. Because I was
yeah,
wondering
all
what
of
I was
them,
kind
the
of
dates
thinking
should
of.
be correct now. If any are up there that's not supposed to be up there, then they would probably have the wrong dates. But I thought I got rid of those.
Okay, so like it said like we discussed something in class and I wasn't sure what it was from, so it was just wrong. Okay.
Gotcha. Yeah. Oh, was this on mastering or was this on Canvas page?
It was on Canvas.
Okay, so yeah, that one's gonna be real. I just hadn't assigned it yet, so yeah, sorry about that. That's actually a neat little problem. I'll go ahead and state it now, you guys. So if you read the chapter 1, they were showing you what the standards are. Yeah, that was one of the ones I had problem with. I thought I posted it last night. Did you check it this morning, Delaney? Sorry, I just stopped right in the middle of the sentence to answer Delaney. Uh, what I
You're
was gonna
good.
say, what I was gonna say I should just check now. Okay. That's weird. So dang it. Now I'm wondering if I posted the wrong one again. I'll check right after class and I'll send you an email as well as the whole class and figure out what's going on. Uh, in fact, right now, let me look. I've got the page up. There is one. Course intro. Dang it. Yep, that's what it is. Yeah, you're right. It did not get posted. That's another one that failed. Sorry about that, Delaney. I will fix that again. Evidently, every now and then I put it up, and it takes a couple hours for YouTube for it to upload to YouTube, at least for my site. So when that happens, sometimes the internet goes out in the middle and corrupts the file, and then I find out the next morning or 3 hours later that it's corrupted and didn't go up. So that's that must have been what happened. All right. So what I was saying about the extra credit is in chapter 1, there's all these introductions where they talk about the various base units that we use, like the kilogram, even though that's got a prefix on it, that's a base unit for the SI, or the Systems International unit system. And they say the fundamental unit of the kilogram is a cylinder that's made of platinum and iridium, if I remember correctly. And it has a very distinct size and geometry to it, specifically because the more surface area an object has, the more contamination it can get. And they use platinum iridium specifically because of its lack of ability to rust and all this sort of stuff. So they have this cylinder of platinum iridium, and it's designed to have a minimal surface area. So the extra credit problem that I'm going to get you to do, let me switch to my document cam, is to compute. This is PHY 241 D01B, and this is 11822. So you imagine a cylinder of radius r and height h. And what I want you to do is find the minimum surface area. Okay, holding the volume constant. Does anybody remember from your calculus days how to find a minimum or a maximum or what we call an extrema? Does anybody recall how to do that? Yes, you even went one beyond what I said. So what about the first derivative? What do you do for the first derivative, Zachary? Or anyone else for that matter?
You just have it equal 0.
Exactly. So you set the first derivative of, in this case, the surface area equal to 0. But you'll see the surface area is 2 times pi r squared. That's 1 for the top and 1 for the bottom, plus 2 pi r h. That's the actual surface area S. So you actually got two unknowns. You got an R and an H, right? But you also have the volume, which is equal to pi r squared h, right? So what you're going to do is you're going to set this as a constant, and then you can solve in terms of r or h, plug that back in there, so you only have constants plus whichever variable you do. Okay, so you've got to first find the extrema, and then second, confirm that that extrema you found was a minimum, not a maximum, and not a inflection point. Okay, so it's basically two parts you got to do, and that's on week 1 module for extra credit. Okay, and when I do this, basically what I do is, like I told you guys, homework problems, I'm going to drop, I think homework says, I think I said I'm going to drop 1 or 2 of the lowest. Every time I introduce a extra credit, I add 1 to the number of homeworks I'm going to drop. And if you don't do it, you'll get a 0, but it won't matter because I've dropped an extra thing. If you do it, then of course your grades are just getting better. So that's the extra credit assignment that is listed as 8/23. I'll fix the date now that I've introduced it. But thank you for bringing that up, because I did want to bring it up today since I didn't get to mention it in class. So this should be in week 1. You'll see an extra credit assignment that's posted in the unit. It might be invisible right now, in which case the student that asked about it might have saw it somewhere else. But either way, it'll be up there, and I usually give you about a week to do it. So that's a good little practice with your calculus, because one of the things of calculus-based physics is we're doing calculus. Yay. Anybody have any questions?
Yeah. Do we have our answer in terms of volume? Because even though it's a constant, it still when we optimize, it still plugs back in. Like we'll have volume.
Right. So what you're going to have is a relationship between R and H. That's the final answer. But you're going to have to, of course, show me the work. And basically all you have to do is work it out on a piece of paper neatly, take a photograph of it, and upload the photograph as a JPEG or preferably a PDF.
So you said the relationship is between R and H?
Yeah, like it'll be, you know, R has to be 1/10 of H, or H has to be, you know, 5/7 of R, or something weird like that. And I think your book might even mention the actual correct answer.
All right.
Okay. So it's a neat way you can do multivariable calculus without actually doing what's necessary of multiple variable calculus, which is normally an advanced calculus course. But by me giving you these two equations and telling you hold this one constant, you've reduced this 2 variable equation to 1 variable. Anybody else? And yeah, don't forget your second derivative test. By the way, those of you who might be rusty on that or occasionally forget, The only thing that keeps me straight about that is I always remember y equals x squared, because that's a function everybody should know off the top of their head. You know, it looks exactly like this. There's no ambiguity whatsoever as to whether that point right there is a maximum or a minimum. And in fact, when you do the second derivative test, you find out that exactly what is required of the second derivative test for it to be, in this case, a minimum. All right, so now what we're starting is chapter 2, which is describing motion kinematics in one dimension. So we're basically starting to teeter on introducing vectors in a weird way. So we're doing it in one dimension, and what I want you to recognize is in one dimension, a sign is really all you need to indicate direction. So let's imagine every morning when you get up, you're standing at the origin of a number line, okay? If you walk in the direction that you happen to decide to be the positive number line direction, then you are going in the positive direction, and your final position minus your initial position, which is something we call our displacement. So I'm going to write this down and we'll bring it up in a second. So displacement is defined to be delta x, which is x final minus x initial, again, r. So if you did the final position, it might be x equals 3 meters minus the initial position, which was 0 meters. Then you're going to get 3 meters minus 0 meters is positive 3 meters. And that positive sign, though you usually don't write it because positive you don't have to, that indicates the direction in which you walk. Now, if you get 3 meters away from your bed or whatever, and then realize, oh crap, I forgot my phone, you might walk back 2 meters and then just reach over and grab the phone because you're gangly and your arms are a whole meter long or something like that. So in that case, you got to x equals 3 meters and you turned around and walked back 2 meters. Now, in that case, your position, your displacement is again final position minus initial position. Your final position is now 1 meter, and your initial position is still 0. That's when you stood up. So 1 meter minus 0, you're still a positive displacement. Okay, so that is still a positive direction you've moved. Now, if you then realize, oh crap, I need to get behind the bed because my charger fell back there, you might walk an additional meter backwards and then another meter backwards still to get behind it. If that's the case, then you've now reached to x equals negative 1 meter. Now your displacement is negative 1 meter, that's the final position, minus 0 meters, which is the initial position, and you get a negative 1 meter. That is a displacement that is negative and it has a negative sign. So it doesn't mean that you walked a negative distance, because distance, which is really the magnitude of the vector quantity, can never be negative. There's no such thing as negative distance, no such thing as negative magnitude. Distance, I'm writing this down, I'll show it to you in a second. They're never 0. Now, in this case, you could actually say, well, my total distance walked was I walked 3 meters, and then I walked 2 meters back, and then I walked another 2 meters back. So my total distance traveled was actually 3 plus 2 plus 2. So that'd be 5 plus 7. So 7 meters is my total distance traveled. That's something entirely different than your displacement. That's the total distance traveled. But it turns out when we start to cover velocity, velocity is going to be your displacement divided by the time taken. So when you got back to x equals 0, your displacement was really 0, because it doesn't matter what you did in between 0 meters and getting back to exactly 0 meters, your total displacement is 0. So that's kind of what we're leaning at now. So let's look at some examples of how this plays out. So what I said for starters was there's a concept called displacement. That displacement is defined to be delta x. Whenever you see this delta is the capital delta, the 4th letter in the Greek alphabet, and it always indicates final minus initial, or final minus initial. These are some of the ways we write final and initial. If we don't put any subscript on it at all, it's understood to be the current one or the final one. If we put a subscript on it that's 0, that is another word for initial, but really we use the letter 0 or the number 0 specifically because that's supposed to be the x at time t equals 0. If I put an I, that means initial. So you might not have started your stopwatch at t equals 0. So by writing I here, it just means, okay, when we first started looking at the experiment, and then F is final. Okay. And what I just told you was the distance really can't be negative. It never can be negative. And that's sort of equivalent to magnitude. Okay. Because they're both never 0. Okay. Now, in reality, I'll put a little squiggly and just say sort of. Because when we start doing things like this, I'll walk, let's say, due east 3 miles, and then I walk due north 4 miles. Okay. The magnitude of my displacement will be 5 miles. So I just actually walk this and this. So my distance in that case equals 3 miles plus 4 miles equals 7 miles. My magnitude of my displacement notice I put a little arrow over top of it. Okay, that's how we indicate something's a vector. That is just 5 miles. And since I'm talking magnitude, I could also say like that. And I don't want to set that equal to it. I'm going to say is instead. Because delta x being a vector means I'm not allowed to set that equal to 5 miles because a vector has to have a magnitude and direction. And that is only a magnitude or a distance. Okay, so that's what I mean by it's sort of equal. So we're going to think of this as a fundamental idea. So there's an idea about the distance traveled. There's an idea about the magnitude or the displacement. Displacement. And really, like I said, displacement is equal to delta x. And that's a vector quantity, which again, for one dimension, just means a plus or minus sign. Okay, in 2 dimensions, it's going to be stuff like, you know, this is 53.1 degrees north of east. But right now, we don't need to worry about that. So there's 2 ideas, a distance traveled and a displacement, that mean 2 different things. And they introduce a concept of position like you would have on a number line in 1 dimension. So now you can consider graphs like this, and I'm actually going somewhere with this, believe it or not. You can consider a graph like this, where this is time on the horizontal axis, measured in, say, seconds, and this is your actual position, measured in meters. So x is really position. So this is a position versus time graph. And whenever you look at a graph, any graph from now on, hopefully you've already been doing it because you've already had, you know, some science courses in the past. But whenever you look at any graph, the first thing you need to notice is what are the axes measuring. So this says x, which I told you was position. This says t, which I told you was time. The next thing you need to look at is what are the units. This says meters, this says seconds, so it's in meters per second. And then the third thing, so first is axes labels. Second is label units. And the third is the scale. Because if you have to go between 2 numbers, like between 10 and 100, you might need to estimate whether it's, 150 or 900 or whatever. And some graphs you'll see will go, here's a distance, let's call that 1. And then I take twice that distance, I'll call that 2, right? Other graphs, you'll see this 1 would say 10, or this 1 would say 1, for instance, and then twice would say 2, and then 3 times would say 1,000, and then excuse me, this twice would say 10. The third one would say 100, and then this fourth one would say 1,000. That's a logarithmic graph. And then not only that, they can both be 1, 2, 3, 4, 5, 6, but a horizontal distance right here might be, say, 1 unit, whereas this big thing vertically is 1 unit. So all of those different things can alter how you interpret a graph. So that's the big things you want to always do when you look at graphs, is try to make some sense of what they're saying. This one I'm going to try to draw 1-to-1. So in that case, when you if you see something going at a 45-degree angle, if it really was truly to scale, then it would actually exactly have a slope of 1. That's the ideal scenario and the easiest to deal with. But if I made a graph like this and I said that after 1 second an object had went a distance, or actually, let's say after 2 seconds an object, no, I don't want to do that one either. Yeah, let's say after half a second an object had traveled from 0 at 0 seconds to a distance of 1 meter at a half a second, and then after 1 second it traveled a distance of 2 meters, and then after 1.5 seconds it traveled yet another meter. So this is roughly here, and then after 2 seconds it traveled yet another meter, like that. And of course you would say the graph would look like this, and I'm going to continue that and say it went on forever. Now, the one thing you might notice is, in terms of, remember in algebra, you had y equals mx plus b for linear equations. This is clearly a straight line, so it should have an equation like y equals mx plus b. Where, does anyone recall what this m would be and what this b would be?
M is slope and B is y-intercept.
Exactly. And this is the y-intercept. Okay, can anybody just look at this graph and tell me what the y-intercept is?
0, 0.
Exactly. So that's often written, as she said, b is equal to 0, 0, or someone might also say b implies y equals 0. Both of those are acceptable, at least in my class. Okay. Luckily, some of these questions will be done, if you have something like that, it'll be done in multiple choice, so there's no ambiguity. Now, the other thing she said was the slope. What I want you to think about first, though, is what is the units of the y-intercept, and that's exactly why I gave you this version here. Okay, can anybody tell me what the unit of the y-intercept would be in this version of y-intercept?
Would it be the distance? Is that what you have on the y-axis?
Yeah, that's what I have on the y-axis. So what would the unit of that distance be?
Meters.
Exactly. Now, the way we separate units from the actual quantity, remember I told you just put a box around it. So that's the way I could write that, y is in meters. The reason why I want you to realize that is a lot of people don't really get, even after, pre-calculus and all that, they don't get that when you graph a line in two-dimensional space, you're really telling someone that there's an equation that exists that relate t and x in this case, such that every t and s that satisfy that equation is a point on this line. No problem, Robin. Thank you. So every point on this graph is a t and s that satisfies the line. In this case, you could actually see that the line is x is equal to, you guys can probably calculate the slope. Can somebody calculate the slope of this for me? And don't forget the units. Remember, units are important in science.
Two meters per second.
Exactly. So notice I went ahead and changed the y to the x because that's what's on the vertical axis, and I changed the x to the t because that's what's on the horizontal axis. And I went ahead and included the intercept. Now, the reason why all this is going, I wanted you to see something. One, I think you all understand how fast this thing's going. How fast was this particle going if this is the real graph of it? Anybody know? After 1 second, it had traveled a distance of
2 meters.
2 meters. So in fact, yes, like Zachary posted, it's 2 meters per second. That's not a coincidence that that's the slope. That's a big thing to understand here. 2 meters per second equals the slope, and 2 meters per second equals the constant velocity, or constant speed. That's not a coincidence. So it turns out when Galileo was threatened, he was taken before a court, and they were basically saying, okay, well, you've been teaching A, B, and C, and you've been interpreting scripture. That's not okay with us. You must recant your position and apologize to the court, and we'll decide what to do with you. And he's like, no, I'm not going to do that. I'm a bad A, and I'm not, ain't nobody gonna mess with me like that. And then they, of course, showed him the instruments that they would use to rip his organs, his entrails out of his gonads, and he quickly recanted. Okay, he was aware of Giordano Bruno's fate just a little while prior to that, so he actually recanted, and he was told he couldn't study astronomy anymore. So he said, well, I seem to understand, at least in personally to himself, he said, well, I understand that clearly the satellites of Jupiter, which he had named the Medicean moons, but we call the Galilean moons, they were actually following along, keeping up with Jupiter as it orbited the sun. So he wanted to understand motion. So he went in and started studying motion. Well, the problem was, if you drop an object, it's hard to tell whether it instantaneously goes some speed and travels that same speed all the way down, or whether it's speeding up. So he had a real problem with that, but he realized that basic trigonometry and ratios of, opposite to adjacent and stuff like that were directly related to the vertical motion. So he decided to do everything on inclined planes, very gradual slopes, for instance, like this. And then he could realize the slope along here, how that's related to the vertical acceleration, and that would be able to work. And he even had to invent his own timepiece, because they didn't have anything but those basically glass containers where sand would fall down in them. That's all their timepieces were, and they're not very good. So what he created was a water clock, where basically what he would do is, the instant he wanted to start a timer, he would open this valve and water would start to trickle into a box whose mass he already knew. And then when he wanted to stop time, he would close the valve, and then he'd weigh the box, subtract the mass of the box, and use that unit of mass of water to relate to some time. And then he could find, well, this is twice as long as this is 3 times as long as that. So that all worked. So that's how he studied motion. And what he discovered was, or invented, was an idea of the term velocity and speed. And what he said was, speed is equal to distance traveled divided by time taken. That was his definition of speed. You can see the slope has that type of unit. It has distance over time. And in fact, speed has the units of meters over second. So that's distance over time. So that really was. And in fact, he went on to define constant speed as moving the same distance during a specified time. So what I mean by that is if I look here and I consider 1/2 second intervals, then at t equals 1/2 second, I had moved 1 meter in 1/2 second. So 1 meter divided by 1/2 second is 2 meters per second. But if I go up here to say the 2 meter mark or the 2 second mark, I see that I have in fact moved 1 meter in 1/2 second. So again, I get the same time or distance traveled in a specific unit of time. So for instance, in our 1/2 of a second, we consistently get 1 meter. That means it's constant speed. We use the symbol S often for speed, and that works just fine. Okay, so because of this graph, we see that every 1/2 second it moves 1 meter, and you can continue on with all these dots if you want to. And that is the picture of constant velocity. Notice I just flipped to the word velocity. Now, the difference is velocity is equal to, and I really should put a bar over this to mean average, because we're going to get to a more general case in which every 1/2 second it's not going to go a whole meter. So I'm going to do the same thing. Average velocity is displacement over time. And the difference being is, again, you're going to take the displacement. So in that case, like where you walked 3 meters and then came back 2, then the displacement in that case is literally only 1 meter. So your velocity over that time would be 1 meter divided by however much time it took. And in fact, when you came back to your bed completely to x equals 0, your velocity is going to be 0 no matter how long it took. So that's sort of the difference between one of the differences between velocity and speed. Often people will say speed is the magnitude of velocity, and that's not exactly true, because again, the displacement could be 0. And clearly the average speed over that time is not 0, so it can't be that. So we say the average velocity is the change in position over change in time. And since you know this, can anybody guess what the actual velocity at any instant is? From your knowledge of mathematics?
The derivative of whatever your equation is going to be.
Exactly. Exactly. So the velocity actually turns out to be the limit as delta t approaches 0 of delta x over delta t, which is in fact defined to be dx dt. Now this is going to ramp up to the same thing when we start talking in 3 dimensions. We'll just use maybe x as a vector, or we might even switch it to r, so people will understand we're not just talking about motion along the x-axis. We're saying r could be any distance away, and r is a function of position. It's a position as a function of time. So we now have, just from everyday life, making sense of something moving, we've reached a conclusion that velocity is displacement over time. That part I had to define for you, but this part you already knew. And you might even just say, okay, well, s is equal to distance over time. And you might think, oh, crap, these are all new concepts I know nothing about. But I doubt that's the case, because you all have more than likely either driven a car or own a car. And if you look at your speedometer, what are the units on your speedometer? Anyone? What's the units on the speedometer of a car? I don't care if you're in Europe or here. Yes, kilometers per hour or miles per hour. Here in America, we mostly do miles per hour. Here in physics, we're never going to do miles per hour except to convert it to meters per second. Okay. And notice a mile is a unit of distance. And notice an hour is a unit of time. So this is not something new. And when they say miles per hour, per means divide. So speed equals distance divided by time. That's not some new foreign equation. That's duh, that's my speedometer. Velocity is the same thing. The only difference is we always take the displacement. Okay, which again, in one dimension is kind of stupid, makes no sense, but in 3 dimensions, where you're going things like 3 meters east and 4 meters west or north, that actually makes quite a bit of sense. So that's going to come in more handy later. Now, does anybody know of anything you've ever heard that is a direct measurement of a car's ability to accelerate? A numerical value, for instance.
A 0 to 60 speed?
Excellent. That's the perfect one. There's actually several, but that's the perfect one. So acceleration is the next thing we want to talk about a little bit. And we use the word acceleration in physics, and that applies to everything. We don't really recognize the word deceleration as anything different from acceleration. And often deceleration could mean a negative acceleration, but sometimes it doesn't at all. In fact, there can be a negative acceleration and the object still speeding up. So just be aware to stick to your terms that we've defined for you. So you just said 0 to 60 in okay, that's exactly right. And what that means is your initial velocity, which we call v0 or v sub I, is equal to 0 miles per hour. And then your final velocity, which is also just called v, is 60 miles per hour. Okay, and let's say in 4.0 seconds. That's not a bad 0 to 60 speed. That's probably comparable to a straight off the line Mustang. And maybe if you are maybe a Mustang GT is the way you used to have it, which is slightly more fast, a more powerful one. If you had that, then that's a fairly decent idea. The reason why this is the perfect one, because people could have given me torque, they could have given me horsepower, they could have even given me the cubic inches of the engine. All of those things are things that relate to how powerful it is and therefore how quick it can accelerate. But this is the exact direct measure of acceleration. And you might guess what acceleration is just from this phrase. Can anybody give a guess of what you think acceleration might be defined as? And we'll say A average, just like I said before, V average. Anybody guess? It's okay if you don't. I've never had anybody successfully guess it. So
I want to say speed over time.
close. Will it be okay just to write 60 or 0 over time?
Oh, like the change.
There you go. It's delta V over delta T. And sometimes, by the way, we'll just replace this delta T with just plain T. So just be prepared for that because we do that on occasion. But it's the change in velocity over the change in time. And what I told you about delta is that's always V minus V 0 over, and in this case, you might even say time. So in this case, you would say 60 miles per hour. Notice how my miles per hour is getting shorter and shorter because I hate writing crap. Over 0 miles per hour. And of course, I put the units there just to remind you, you cannot add or subtract things with different units. And then the total was 4.0 seconds. That's how long it took. Well, I like this number, 4.0 and 60, because it looks just like a watch. Everybody knows, of course, when a watch second hand goes all the way around, it's covered how many seconds?
60.
Exactly. So 60 seconds. And then if you break that up into fourths, how long is this one?
15.
15 seconds. So we immediately know that the acceleration is 15 miles per hour per second. Now, if this were truly constant acceleration, so here I am defining constant acceleration like I defined constant speed earlier. If this was truly constant acceleration, then at t equals 0 seconds, the car would be moving v equals 0, right? And then at t equal 1 second, the car would be moving at 15 meters or miles per hour. Okay. And then at t equals 2 seconds, it'd be moving at 30 miles per hour. At t equals 3 seconds, it'd be moving at 45 miles per hour. And at 4 seconds, it would be moving at 60 miles per hour. That's the way I like you to think about acceleration. That's why I made this stupid looking unit, miles per hour per second, miles per hour per second. And your book is going to use meters per second squared, which is exactly the same as meters per second. Okay, but I like you to think of it as meters per second every second. The reason why is you can think, okay, if something's really going in a constant acceleration of 15 miles per hour per second, then you can immediately predict the speeds for some time later. 0 is going to be 0, 15 is going to be, or excuse me, 1 second is going to be 15. Then I add another 15 to get 30, another 15 to get 45, another 15 to get 60, another 15 to get 75, so on and so forth. And it gives you some physical feeling for what acceleration means. Okay. So constant acceleration means the velocity changes by the same during any specified time. In this case, we chose a specified time of 1 second, and we found that the velocity would change by 15 miles per hour each of those. Now, that's not really how a car accelerates. In fact, it's probably a buttload of acceleration right in the very, well, maybe from the half a second mark to the 3 second mark, it's a buttload of acceleration, and then it starts to slow down. The acceleration actually decreases from probably the 3 seconds to 4 seconds. And it can continue to accelerate, but it's going to do so slower, or the acceleration is going to be lower, specifically because the car does have a maximum velocity that it can reach, right? So even though that's not necessarily a physically real situation, for a car having a constant acceleration, it's a wonderful model for us to think about acceleration. So when you see the average acceleration is delta V over delta T, what do you think the instantaneous acceleration would be? Anyone? Bueller?
Is it just delta A over delta T?
How about how did I go from average velocity to instantaneous velocity?
dv over dt.
There you go. That's the difference. I think you were thinking along those same lines, but you got a little fumbled up in your words. That's why I tried to give another chance. So yeah, if you look at this, what we now determined is average velocity, which I'll just abbreviate this way. Average velocity is equal to delta x over delta t, which again means x final minus x initial over time taken. And then v instantaneous, which is what we call just plain v. We usually don't put a subscript on that at all. That's equal to dx over dt. And this, I remember the first time I was in calculus-based physics and we covered this, and all I could think was, that's the stupidest thing ever. You're not going to just walk out into the world and find x as a function of t. But actually, I was really ignorant. I didn't realize, in fact, there's a lot of ways in which you could be given x as a function of t. Okay, so this is actually a real thing that can be done and will be done. Then we found that the average acceleration was equal to delta v over delta t, which again is v final minus v initial over time taken. And we found that a instantaneous, which again we just leave off the instantaneous subscript, is just dv dt. Okay. We also found out the meaning of constant velocity. And I'll say velocity slash speed here. Okay, just you know the difference between speed and velocity, but I want to show both of them. But really what we mean when we say constant is for a chosen interval of time, for example, 0.5 seconds, every one of the object's intervals, the object will move the same distance. Okay, so if you chose half a second, that's fine. That just means during its motion, when it's actually going in constant velocity or constant speed, it will always cover that same distance in every one of those intervals of time that you measure. So if you look at the 1.3 seconds to the 1.8 seconds, it's going to cover 2 meters, or excuse me, 1 meter is what we had on that other one. If you go to the 8.5 seconds to the 9 seconds, that time it's going to cover 1 meter again. The difference between velocity and speed in this case is not only is it going to cover the same distance, it's going to go in the same direction. So velocity means in one dimension, that just means in the positive direction or the negative direction, it's going to stay the same. In 3 dimensions, it means constantly at 5 degrees north of east or something weird like that. Now we also learned that constant acceleration which is using the vector quantity v. Okay, that's the key thing to remember. The constant acceleration, you basically say the same thing for a chosen interval of time. Every such interval will show the object changes velocity by the exact same amount. So the difference here is velocity dealing with speed, or excuse me, acceleration dealing with velocity versus dealing with speed, is not only is it going to change from the same speedometer reading to another speedometer reading, that's always going to be the same, but also if you happen to have changed by 3 degrees, then you actually are changing your velocity as well. And in fact, that cannot be constant acceleration, because the velocity changing direction is actually causing the acceleration to change. So constant velocity is really when you go from, let's say, every 1/2 second, you go from, let's say, 0 meters per second to 7.5 meters, or excuse me, 7.5 miles per hour. That would be what the Mustang did. Is in the first half of a second, it went from 0 to 7.5. In the second half, it went from 7.5 to 15. In the third half a second, it went from 15 to 22.5, so on and so forth. So that's what constant acceleration means. Now that we have that, we'll say that we are generally deal only with constant acceleration. Okay, now the big deal is we took a derivative of position, we got velocity, we took a derivative of velocity, we got acceleration. It turns out if you take a third derivative of acceleration, then you get something called J, which is equal to the jerk, is equal to dA over dt. That's actually the physical name for it. So people studying in the automotive industry, like engineers working in automotive engineering and stuff like that, they find use for the jerk. But we're not going to touch that. I just wanted to give you that curiosity there. So we're mainly going to study that. So let's look at the definition of acceleration. So we have acceleration instantaneous is equal to dv over dt. And we're going to say this is a constant. Because it's a constant, we can then do this. We can multiply both sides by dt, and I'll get a dt is equal to dv. And then I can take the integral of both sides, and I'm going to integrate this from t equal, or I'll say some v0 to v. Remember, when you just say v, that means v is a function of time or the final velocity, and this is from t equals 0 to t. In that case, the a is a constant, so I just get a times t is equal to v minus v0, which lo and behold, if you manipulate it, it looks like a is equal to v minus v0 over t. That's one and the same. But what we're going to use is the fact that I can solve this for v, and I'd say v, which is actually v as a function of time, is now equal to v0 plus at. So remember me telling you when I first took this course, I thought it was stupid because you're not going to just walk out and get a position as a function of time or a velocity as a function of time. Boom, there it is. Velocity is a function of time. Well, we know that the velocity as a function of time is also dx dt. So I can plug that in and I'll say v0 plus at is equal to dx over dt. I'm going to again multiply both sides by dt. And when I do that, I get v0 plus at dt is equal to the integral of dx. And I'm going to integrate that from x0 to x. And I'm going to integrate this from t equals 0 to t. Well, that gives me v0t plus 1/2 at squared is equal to x minus x0, which lo and behold is another important equation, just like this one was, just like this one was. These are equations that are numbered in your book, so you'll find them on our equation sheet that's in useful documents, course documents. But here's another one. If I solve this for x, I get x is equal to, I usually write it like this. A lot of books have started writing it backwards, but I don't like writing it backwards. But that's the way I generally like to write it. Okay. And a lot of physics courses, the instructors will only allow you to use these equations. They won't allow you to use the one I'm getting ready to derive for you, because these are all vector equations. You can actually translate these to vectors. You put a vector symbol over that v and that v and that a, and you've got a true vector equation. Same thing with this x, that a, that v0, and that x0. Those are all vectors, so it would be perfectly fine. But there's another equation we can take. Let's say, let's call this equation 1. Let's call this equation 2. Let's call this equation 3. I'm going to solve 2 for t. And when I do that, I end up getting t is equal to v minus v 0 over a. Okay, I'm going to call this equation 2 prime. Now I'm going to plug 2 prime into equation 3. And what I'm going to get is x is equal to 1/2 a v minus v0 over t squared, excuse me, over a squared, plus v0 times v minus v0 over a plus x0. I'm going to pull the x0 over here. That'll give me x minus x0 is equal to, now I'm going to say this is, notice what happens when I square this a down here. It's going to become a squared under a. So it's just going to be 1a in the bottom and a 2. So I'll say 2a under v squared minus 2v v0 plus v0 squared. That's what that whole term becomes. And this term becomes v0 minus v, or excuse me, v squared minus v0. No, it's not. I did it right, didn't I? v0 times v. Yeah. v times v0 minus v0 squared over a. Now I can get a common denominator, and then I'll have v squared minus 2v v0 plus v0 squared. Now this one, I have to multiply by 2 top and bottom to get a common denominator. So this becomes plus 2v v0 and minus 2v0 squared, all of that over 2a. Now I've got x minus x0. Hopefully, did y'all see this earlier? I just looked and it looked like it was out of the screen. Anyways, finishing up my algebra, I've got x minus x0 is going to be equal to all this. What I see is a v squared, and then I see a minus 2v v0 canceling out with a plus 2v v0, and then I see a v0 squared minus 2v0 squared, so I just get minus v0 squared, and all that will be over 2a. And then finally, the way we normally express this equation is v squared is equal to v0 squared plus 2a x minus x0. This is the equation a lot of instructors will not let you use, specifically because there's no equivalent to the vector equation. But it is a valuable equation. Notice if you need to find like the final velocity and all you have is the initial velocity, the acceleration, and the distance traveled, you can do that without having to solve for time first. Otherwise, you'd have to solve this one for time or this one for time and then plug it into this one. Or like I said, you could solve this one for time and plug it into that one. That would give you the same thing as well. So this is another what we call kinematic equations. So these equations are called the kinematic equations. Don't get too caught up on the symbols, because symbols are just the things we've chosen to give them. They're quite arbitrary. Like right now I'm saying v minus v0 squared equals 2a x minus x0. I can actually do this exact same thing for y minus y0. I just have to subscript this a with a y saying that this is the acceleration in the y direction, this o with a y saying this is the initial velocity in the y direction, and this v with a y saying this is the final velocity in the y direction. Same thing here. This can be a y, this can be a sub y, this can be a v0 sub y, this can be a y0. Same thing with here. So the symbols are not the important thing, it's their form, you know, initial plus at, initial plus the acceleration times time, 1/2 the acceleration times time squared, so on and so forth. That stuff is what's relevant. And in fact, you're going to find in like chapter, I think it's 9, we'll find exactly similar equations for rotational motions, but we'll replace x with a theta, x0 with a theta 0, v0 with an omega 0, and a with an alpha. And all that's going to get another group of equations that look exactly like this, but using rotational variables. So these are your kinematic equations, and you've got to sort of recall that they are really relating vector quantities. And the reason why I'm even bringing that up is I want you to understand that you can't just always assume gravity is going to be negative if you're talking about an object falling at 9.8 meters per second every second. You can't always necessarily assume that's negative and this is going to be positive, because in fact, if you throw a ball downward and you choose to say the downward direction is negative, because that's the way gravity acts and you just always think of down as negative, then in that case, the A would be negative 9.8 and the V0 will also be negative, because what matters is the direction they're pointing. So gravity pulls things down, so you expect G to point downward. You can choose that direction to be negative, or you can choose it to be positive, in which case this would be positive and this would be positive as well for a ball thrown downward. Okay, all those coordinates you use are completely up to you. All right, so 9:30 to 10:50 is what we're supposed to go. Does anybody have any questions about these equations? Okay, so let's look at some typical problems. First, I'm going to give you a conceptual problem that I don't think your book does at all. So let me turn back here for a second. Now, let's not get get too caught up in the details of exactly where you stand versus where the home plate is when you're playing softball or baseball. Okay. But let's say for a second I'm playing baseball because I happen to know how far away the bases are. I think softball's 60 and baseball's 90, but I'm not sure if I know enough about modern competitive women's softball about whether that's 60 or 90 or 65 or 70 or whatever. So I'm going to take baseball. When the batter is at the plate, we're going to pretend that he's literally at the plate, like literally standing on it, which of course is an out. So you can't do that. But let's just ignore that detail for right now. Okay. So when I hit a ball and I make a home run, because I'm the man, that's what I do. So then what happens is maybe I take 4 seconds to run to first base. And then I take 6 seconds to run to second base. And I take 6 seconds to run to third base. And then I take 10 seconds to run home. So that's 4 plus 6 plus 6 plus 10. So that is 10 plus the 16 plus 10 is 26 seconds. Okay. I just had an average speed of 360 feet divided by 26 seconds. So my average speed is 360 divided by 26. That's 13.84 feet per second. That's pretty fast. My knees are not going to do that. Even that 10-second thing's probably not going to work out for me. Because in addition to being having such bad knees, I also weigh about 260. Well, I like 260 so much I claim 260, even though I really weigh like 280. But anyways, so that's the average speed. What is the average velocity of that same issue? Anybody know? Me running in that circle 90, 90, 90, 90 in 26 seconds. What's my average velocity? Very good. Damien says 0 feet per second. That's exactly right, because remember, velocity is supposed to be this displacement thing. And I started at home plate. That's why I told you to ignore the discrepancies of not being exactly on home plate. And I ended at home plate. So my net velocity would in fact be 0. Now, chances are I am actually going to step over home plate as I run towards first, unless I'm really far up in the batter's box. So there is a time interval over which the actual average velocity would be 0. So that's okay. And then that gets rid of us making up that phony rule. But the deal is, I want you to understand that is a typical conceptual question that they will ask you as one of the factors that differentiates between average speed and average velocity, is that the displacement is what is measured by the velocity. So when you go this way, 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 all velocity cares about is that initial position and that final position. It don't matter how much crap you went all this way. Okay. So that's a key thing to remember. Now let's look at some actual problems. I like to do nice numbers, like in our conceptual physics class. We'll just pretend like gravity, instead of it being G equals 9.8. It's 9.80 meters per second per second. We just pretend it's going to be 10 because the numbers work out so nice. Okay, so that's not a problem. So I'm going to do that for a little bit here, just so we can get a feel for the concept of acceleration quickly without having to do as much math. So let's say we drop a ball. So this is an example. We drop a ball and it falls for 6.0 seconds. How fast will it be going? Ignore air resistance. So I'm going to say A dot R is approximately equal to 0, which is not that bad if you like assume you're dropping a bowling ball or something. Okay. And part B, so I'll call that A. How far will it have traveled? Or how far down will it be? Okay. So I'm looking in part A, I'm actually looking for what is the actual final velocity. Now, this is a tricky thing we've done here, and I've done it on purpose. What you want to do when you read a physics problem that you got to solve is you first want to take those symbols that we had, and those symbols that we've had so far are things like x, x0, v, v0, a, t, delta x, stuff like that. Those are some of the symbols we've come up with so far, right? What we want to do is find all the quantities that were given to us are implied to us so that we might infer them and write them down, and then write down what we want to know and put a question mark by it. So when I said I drop a ball, does that give us any information? That implies, looks like nobody's answering it. That implies V0 is equal to 0. Notice I didn't say any numbers there, but you still were able to get some information out of that sentence. We drop a ball and it falls for 6.0 seconds. So I didn't just get 6 seconds. I got the initial velocity 0. And what is the 6 seconds? Right? T is equal to 6.0 seconds. Did I get anything else? I said we drop a ball. Should we probably assume that we're on Earth? If so, then we can know that the acceleration is going to be either plus or minus g, okay, which equals 9.80 meters per second per second. Okay, and then part A, they're really asking you what is V equal to. So now I'm just going to look through my 4 equations and see if I have any equations that relate the variables I know to the variable I want to know. So I want to know V, so I got to find an equation with V in it. And those equations look to me to be like V equals V0 plus AT, and also looks like V squared is equal to V0 squared plus 2AX minus X0, which, by the way, you can write that as just delta X if you want to save position, save some place on paper. That's fine as well. This one requires me to know how far I've traveled, so I can't use that. But this one has exactly what I need. So a lot of physics when you first start off is just hunting for the equation that relates the things you know to the thing you don't know but you want to know. So I'm going to use that one. I'm going to say V is equal to V0 plus AT. And in fact, I'm going to treat down as positive. So I'm going to say down is the positive direction. So that means A is equal to positive G. So I'll say V is equal to 0 meters per second, because that's my initial velocity, plus 9.80 meters per, oh, excuse me. I forgot I told you I'm going to say approximately 10, just to make the numbers easy. So I'm going to say 10 meters per second times 6.0 seconds. So you see that it's actually going to be traveling at 60 meters per second. And that's pretty good. I mean, actually, it's 10 times 9.8. So it's, or excuse me, it's 9.8 times 6. So it's going to be a little bit less than that, but not a huge amount. So that's a pretty good estimation. What about part B? In part B, they wanted to know how far down will it be. So what they really want to know is either X or delta X is equal to question mark. Okay. What I'm going to do is I'm going to say X0 is equal to 0, then delta X, which equals X minus X0, is just X. Now I'm looking for an equation that relates velocity initially times time and maybe X and X0 So this one, I got this guy right here, but that would require me to use the final velocity that I just calculated. And I don't really want to do that, because if I made a mistake in solving for this velocity, then now I'm going to have a second error in here and I'll get both answers wrong. And the instructor might not see that I did the second part right. So I'm going to look for another equation. And that other equation is x is equal to 1/2 at squared plus v0 t plus x0. All right, sorry, I had a call. I was trying to ignore it. All right, so when I do that, I have x is equal to 1/2 at squared plus v0 t plus x0. By doing the x0 equal to 0, I could just say the distance traveled will be x. I'm going to say 1/2 10. Remember, I'm pretending that gravity is approximately 10 just to make the numbers nice, times 6.0 squared plus 0 meters per second times 6.0 seconds plus 0. That's the x0. Remember, I just assumed that we were starting at x equals 0. Okay, I'll draw a picture of it in a second so you'll understand really what these ramifications are. So with this, I end up getting that x is in fact equal to 1/2 of 10, which is 5, times 6 times 6, that's 36. 36 times 5 would be 150, 180. So it's going to go 180 meters approximately. So those are actually my answers. Again, I'll put that over there just because I approximated G to be approximately 10. Now, what my drawing was is you might have considered it to be like this. You might have said, okay, I'm standing right here and I drop a ball like that. And what I did was I said, this is my positive x-axis. Maybe this is my y-axis. So the origin is actually either the center of the ball or the bottom of the ball, whatever, doesn't matter. As long as you consistently measure it to that point, you'll be fine. So what we found was that it'd be traveling at 60 meters per second after 6 seconds, and that it would have traveled a distance 180 meters after 6 seconds. But let's do something neat. Let's add a part C. So I'm going to add a part C and say, how fast after 3.0 seconds, and then add a part D and say how far after 3.0 seconds. Okay. Well, what I want you to see, rather than just blindly plugging in this equation, what I'd like you to see is that this is a linear relationship. And that it's even better than that. It's a proportional relationship because V0 was 0. If you cover up that V0, you just get V equals A times T, which means that velocity is directly proportional times time. It's directly proportional to time. I call that thumbs up, thumbs up. As time increases, velocity increases. So for part C, it's half the time. So I expect half the velocity. So I'd say V equals 30 meters per second for part C. And in fact, if you work that out, you'd see V is equal to 0 plus 10 meters per second every second times 3.0 seconds, and lo and behold, you get exactly that. Okay. Now that's sort of the concept. When you have an initial velocity of 0, the acceleration, or excuse me, the velocity doubles every time you double the time. If you triple the time, it triples it. If you quadruple the time, it quadruples it. If it's not even proportional, though, it still doubles it and triples it, but you have to add the initial velocity each time. So that's conceptually what's going on. Now let's look at part D. Now part D, I noticed since I had the initial velocity equal to 0, this equation right here just becomes 1/2 AT squared. So you see that X is proportional to time squared. X is proportional to time squared. That's thumbs up behavior again. But this time, if you double it, you have to quadruple it. If you cut it in half, you have to cut the distance in fourths, and so on and so forth, right? So 1/2 the time. So I expect 1/4 of the distance. Or X is equal to not 180 and not 90, but 45 meters. Now let's check with our equations. X is equal to 1/2 10 meters per second times 3.0 seconds squared plus 0, and 5 times 9 is in fact 45 meters. Okay. So that's me choosing to do this as a conceptual problem as opposed to a purely mathematical problem, just because I wanted you to understand what Galileo discovered when he came up more or less with these equations. He found that the acceleration, when it was a constant, basically behaved in such a way that the distance went like time squared. Whereas when it was a constant velocity or a constant acceleration, the velocity went like time linear. Okay, so that's some typical problems that you might be asked to do. Now I only got like 2 minutes left, so let's now try throwing a ball up. Again, I'm going to use the 10. Throw ball upward at 20 meters per second. How fast after 1 second, and how far after 1 second? Okay, so part A, what we know is the ball is thrown upward. So V0 is actually going to be 20 meters per second, and it's upward. So I'm going to put a plus there. I know that A is equal to negative 10.0 meters per second. Again, we're just using that as approximate. You should never use 10 in your problems that you're solving. You should always use 9.8 unless it explicitly tells you otherwise. And then T is equal to 1.0 seconds. Again, I'm trying to find the final velocity. Well, the final velocity is equal to, the final velocity is equal to the initial velocity plus AT. And this is why you had to have the opposite sign here. You're going to have 20 meters per second plus negative 10 meters per second times 1.0 seconds. So it's going to go to 10 meters per second. And that's what's going to happen every second. Every second, the velocity is going to decrease because it's proportional to t. The velocity is going to decrease by 10 meters per second. Similarly, X is equal to 1/2 AT squared plus V0t plus X0. So in this case, we're going to get 1/2 of 10 meters per second times 1.0 seconds squared. And this is going to be a negative here. And then it will be plus 20 meters per second times 1.0 second. So this will be -5 times 1 will be -5, and this will be 20, so it'll be 15 meters. That's it. Okay. All right, that's enough for today. Time's up anyways. Thanks for coming, everyone. Yes, if you do 9.8, you would have gotten 58.8 meters per second instead of 60 meters per second. That's the only difference. We'll work some more examples next time. I've covered the vast majority of chapter 2 already, believe it or not. So make sure you read over it, look at those examples, and then be prepared for our examples next class. Have a good one, folks.
Thank you. Same to you.
Take care.
Take care.
So
I'll stick around in case anybody has any questions, of course.
So does that mean for lab today, it's going to be less about like a lecture and more about just the lab?
Yes, it'll all be about lab today.
And do you know if the TCC, I can definitely look this up, but do you know if they're open for picking up a book? Because I haven't picked mine up yet.
Far as I know, they are. You have to wear a mask, but you might want to call Barnes and Noble bookstore just to be safe. But I'm pretty confident they are. Okay.
Yeah, because it's been kind of a struggle because I don't have a book yet, so it's kind of, I don't know.
Yeah, that's not so easy. Remember, you can still sign into MyLab and Mastering, and I think you even have access to the book there. So at least do that.
Okay, thank you.
No problem. Emilio, Jessica, Julia, anybody?